Hello everyone. In this video, we'll continue to examine topic 5.1 electric fields, and in particular, we will begin to examine electric current. Okay, so up to this point, we have been primarily concerned with what is known physically as electrostatics. Where electrostatics means that the charges aren't moving. Static means unchanging. In this case, it means not moving. We are going to begin to transition into what is known as electrodynamics, so moving charges, okay? With no sort of attempt to hide where this is going, moving charges tend to be very useful in ordinary everyday life, as moving charges are better described as electric currents. Where do these come from? Well, we have seen that an external electric field produces a force on electric charges. And this force on the electric charges, we have done a lot of calculating, we've done a lot of explaining of, but that force is going to cause them to accelerate and ultimately to move. So if you apply an external electric field to charges that are free to move, they will move. And that moving charge is the essence of this idea of electric current. If the external electric field is maintained, so this is key, you have to maintain it within the conductor. You have to apply it to the conductor and maintain it. Okay? Notice this differs from our last topic because in our last topic we used that idea of the external electric field caused by these charges on the outside, but then the free charges inside could move in order to cancel it out. That was the key to recognizing that the electric field inside a conductor was zero. In what we're about to study, we're going to consider a case where you simply maintain that external electric field. You don't allow it to ever drop to zero. You maintain it via an external power source. And we'll talk about how to do that eventually, although we're not there yet. So we're going to maintain an external electric field inside of a conductor. We're going to have that conductor be long and thin and probably in a cylinder or a tube, and we're going to call that cylindrical tube of metal conductor a wire. And so if we maintain electric field in that wire, from a positive end with electric field going away from that to a negative end with electric field going towards that, then the charges inside the wire will feel that electric force, Fe equals Q times E. And in doing so, they will move. And that is the essence of electric current. So, electrical current, aka electricity, although you actually won't hear me use that word very often, just because it's a little bit ambiguous. But electrical current is given the symbol I. I don't know exactly why that is, although I suppose I could look it up. But it's given the symbol I. Remember that capital C is already taken for Coulomb. And electrical current is defined as the rate of flow of net charge, okay? So you could even put the word positive in here, per unit time, okay? Remember that rate just means per unit time. We almost never write this out. We almost always give this definition in symbols. I is defined to be delta Q over delta T. For those of you with differential calculus at this point, I is dq dt. It is the rate of change of charge through a particular point. So as charges flow, okay, in that wire, that tube-like wire, a certain amount of charge will pass a particular point in a certain amount of time. That delta Q, amount of charge, divided by that amount of time, delta T, is current. That's the idea of current. And the unit is the ampere, given the simple capital A, where 1 ampere is 1 coulomb per second. So, certain amount of charge per second. Electric current in the IB, although there are some interesting consequences of this, is a scalar. So, a certain amount of electric current, regardless of what direction it's flowing. It's how much charge is passing a particular point per unit time. This is given sometimes as the rate of flow of net charge. And something I'm not going to be very good about, but I should at least mention, is that in discussing electric current, it's good practice to say that electric current exists and charge flows, but current can't, technically speaking, flow. So current can be increased or decreased, but current can't flow. Charge flows. And when charge flows, you get a current. Now, I will say I am guaranteed going to say current flows at some point, but I just thought I would mention that particular subtlety. So this is our definition of electrical current, and the charge then transferred in some delta t is delta q equals I times delta t. So if you're given the current, let's say it's 10 amperes, and the time, let's say 4 seconds, then the amount of charge transferred by a 10 ampere current in 4 seconds is 40 coulombs. Okay, so these two equations are very much related. The definition of current on the one hand, and then how the amount of charge transferred in a conductor, usually a wire, is equal to the current times the amount of time that it has elapsed.